Well, hello, hello. Okay, so I'm always like looking to change up what I'm doing, how I'm doing things. So this data structure is going to be the linked list, and what I'm interested in is actually tackling a coding problem while at the same time implementing the data structure. So I'm using my trusty, handy dandy cracking the coding interview book, and I'm here on the chapter called chapter 2 called linked list, and I'm doing problem 2.2, and the problem here is return the kth to last element. So implement a algorithm to find the kth to last element of a singly linked list. There are some solutions here, and I'll actually there's a solution. I'll definitely check it out afterwards. But I just want to just see what I can do right away. So I'm going to create my my file here. So this is my hello. Okay, this is my linked list.js. Okay, and let's start with the class called let's start with a node class. For doing my node class, it's going to have a basic constructor, maybe some value, and this dot val equals val, and then it will have a reference to the next value, which in this case is null in JavaScript. Okay, undefined, null, whatever. And that's kind of it. That's very simple, right? Okay. So now I'm going to have another class which will be kind of like a wrapper for the linked list, which I'm going to call linked list. Sure enough. And to be sure, I want to. So there are going to be some constructor. Maybe it has an initial value. So this dot root equals a new node, which has a value, for example. That might be a way I want to start it out. Again, depends on your implementation. Maybe you just want to have a empty root and then you add to that. That kind of depends on what you want to do. Actually, maybe I should do that. No, I don't want to do that. The heck with that. Just like adding more complexity unnecessarily. So here I'm going to have a LL, which is going to be my new linked list, which I'm going to give it the value 5 for whatever reason. And I'll console.log my ll.root. Okay, let's see how this works. Let me clear this. This is my last video. Alright, so this should work here. So I can say node.js links list. And I print out my root node, which is value 5, with nothing at the end of it. So I just set up a single node, so that's pretty basic. And then, well, now we can talk about adding to it. So when we talk about adding to it, you have to think about traversing this thing too. And it's pretty straightforward. It's literally just keep going down your linked list until you get to the end where there's a null value. And when you get there, you're adding a new node onto that reference. So that's all we gotta do here. So I'll make a add, or maybe I could do append, because you're appending to the end, I guess. So append some val. And oop. I'm also noticing I'm getting quicker in my typing. It's been a while since I've had a lot of time dedicated just to coding, so it's really good to have some practice just being on the keyboard. It's been a while. Let me do a const new node. New node of the val. I'm not implementing any restriction on these values or anything. Just store it. This is just anything really. You can have an object or value or whatever you want here. It's just whatever the element or whatever kind of data you want to store. So, excuse me. So we can do while let cur equal this dot root. So while cur JavaScript, while you have a next, so while you have a reference to the next thing, then you haven't found the end of the linked list at this point. So we can just say cur equals cur dot next. Okay, and once this loop exits, that means that you are at the tail end of the linked list, and then we can literally just say cur dot next equals the new node. Okay, and let's look at doing that here. We do ll dot append, and let's add the value 10. Okay, and let's look at this. All right, sure enough, we now have the root, which is still 5, and then it has its next as the node with the value 10, and then that has a reference to nothing because that's where it ends. So that is one way of doing it. So I'm just gonna add a bunch of stuff here. I'm gonna add 20, 30, 40. All right. Let's see what that looks like. So it's gonna look kind of messy because it has like a lot of stuff. It even like cuts it off here. It just says you have more nodes, but just 5, 10, 20. It keeps going. So that is looking good. So now I need to think about this this question about getting the kth to last. So kth to last is some. I'm gonna call it here. So this is like get kth to last. Okay. So what this would look like is if this number is 2. So let me just do that here. So if l.kth to last, get kth to last, and I put the number 2. In this case, the second to last would be this one. It would be 30. All right. So let's do this. So I'm gonna have my my slow runner equals this dot root, and I'm gonna have my fast runner still this dot root. Okay, that's fine. The current distance was 0, so there's no distance between these two at this point. All right, so we'll say while fast runner dot next. We know that we are not at the end, so we can say fast runner equals fast runner dot next. So I basically so at this point, what I'm trying to establish here, I should like really write this stuff out. So I'm trying to establish proper distance between runners. Okay, so if let's say k is like 10 and you don't have 10 elements, then you're gonna have problems with like knowing what the 10th to last is, right? And if that is the case, then we're gonna have some problems. So if you can get to the next one, then I know that I can do cur distance plus 1. So if it's 2 ahead, wait, is it? I guess it's k minus 1, really, right? Okay. Current distance plus 1, and cur distance is less than k minus 1. The second you get to k minus 1, then you are in the right spot. So here, if cur distance is not equal to k minus 1, I need to put my statement here. Then I will throw. I want to throw an error. Like there's no k. Do I want to throw an error? Or do I want to return like none? I think I want to return null, actually. Null lowercase, because we're in JavaScript land. Okay. Couldn't get enough. Okay. There weren't enough nodes in the list. Okay. So when are there enough nodes in the list? Well, that's the point. We can now literally just keep going, and this time it's kind of a similar implementation here, where we can keep both runners going. So now that the slow runner and fast runner are in lockstep, effectively, we can just keep them going, and then slow runner equals slow runner next, and then we just return slow runner once the fast runner has met its end. Okay, so let's see what this looks like. So here I'm going to kind of copy that. So this should give me the 30, I think. So let's try that out. Hey, all right. Slow runner equals this dot root. Slow runner is not defined. Oh my goodness, man! Python has been destroying me in JavaScript. I swear. Okay, fine. Anyway, let. So now we can do the thing. We can do the thing by calling this thing. Hey, I got 30. It works. Oh my god. I shouldn't be surprised by these things. I really shouldn't, but I am just always so happy when things just work out. And so this time it returned to me the 20, which has the 30 and the 40 after it. So this is the third to last, correct? This is third to last. This is the last, second to last, third to last. Hey, all right, it worked out. Deleting a node, because that's where you have these like references. You might have these leaky references that you want to be looking out for. So I'm going to quickly go through a deletion method. So delete. So you want to delete like a value. So you basically need a traverse. So we need a traverse until value found. Okay. So I need to keep track of parent. And then reset parent.next to found node.next. And I think I can just delete the found node too. Like when I say delete, I mean like the function, the method delete in JavaScript. Found node. Okay. So we have our. I'm going to keep let parent equal this dot root. Okay. There's some minor things I'm not like really doing here. So one thing I want to keep track of is, so the thing I'm not implementing is the fact that like this dot root might be null. I do have that as part of the constructor here, but like I was mentioning before, that's just my own implementation. Sometimes you start it with null, and you will have to include all those checks. That you will have to include that check anytime you like do anything, basically. Because this get kth, I'd have to say, hey, is root even defined? And if not, then give an error or something. So it should work fine, but I am always in the back of my head thinking I'll have to keep track of all possibilities, basically. All right, so parent is the root, and let child equal this dot root as well. Or I should say this dot root dot next. Dot next. So if so literally just this dot root dot next. So if you don't have if you don't have a next, then just return. I don't think I need to go through any of this. It'll give me errors if I do anything else. So if you delete, oh wait, what if the root? Oh god, this is the annoying thing. Yeah, what if the root is the thing you're deleting? Okay, fine. That is the situation I'm thinking of. I knew I was forgetting something. That val. If this dot root dot val equals val, then then we have to basically just reassign this dot root. Okay, so this is another problem. Okay, I'll talk about this in a second. So this dot root equals this dot root dot next. Okay, and then I can just return from there. Okay, so here's the issue. Because this exists, because I can delete the root technically, and the root could technically be the only remaining node, I might have a linked list that has a root of none. Period. So that means any other situation that I have set up, I need to actually check. Just because of that, just because delete exists, I need to have this set up. So I need to have that check, even though I implemented it to ensure that there's a root node always. That's not always going to be the case because delete technically exists. So this dot root, if this dot root doesn't exist, return null. Okay, basically I'm going to kind of add that in everywhere. So for my append, append is the only situation. So append is a new node. If the node doesn't exist, so if the root doesn't exist, then I'm just going to add this dot root equals new node, and I can just and I don't need to do anything there. I can return here. Yeah. Okay, so that makes sense. Okay, I'm just going to quickly double check to make sure my code is still working otherwise. So I'm going to just rerun it, and hopefully it doesn't break. Okay, still works. The git kth is still working. I'm gonna recheck this when I finish the delete method to make sure it's also going to work even with empty node, empty root. Okay, so the child equals this dot next. Nope, is this root, or I should say maybe parent dot next, just as really explicit. Okay, so if root dot val equals, so if the root, oh my god, even if I delete val, even for delete I have to take that into consideration. Oh my god. Yes, so if root doesn't exist, I am returning this dot root. So return root, which should be null, but I'm just being explicit that this function should return the thing that was deleted. That's usually a pretty good idea, just in case you want to keep track of that reference in another way. It's a good idea to return the node that is removed. Okay, so if this dot root equals val, so this is root undefined, root is null, root doesn't exist. So this is root being removed. So I need to keep a reference. So let const ref reference equals this dot root. Then I assign this dot root to the next value, which could be null, it could be anything, it doesn't really matter. Then I want to return my saved reference, and the whole point of me saving the reference was so that I could return it explicitly for the user to do whatever they want with it. I just want to keep the reference. Okay. Okay, now that all that's done, then we could look at the parent and the child. So the parent necessarily is not the value. The child may or may not exist. So while child, so if the child doesn't exist, we are returning the thing that was removed, right? So I return child, which might be null, and that's fine. I'm like doing this a little bit sooner. So this is me reversing until value found, reset parent to next, which is going to be in here, and delete found child. Actually, I don't want it. So I take that back. I don't want to delete that reference from memory. I actually want to return it, and the user can do whatever they want with it. If they do nothing, then garbage collection will clean up anyway. So while child, while child exists, we're going to say, okay, parent equals child, and then child equals parent. I need to keep a reference here. Const child ref equals child. Okay. Or do I mean parent? I'm swapping the okay, I'm doing two things wrong here. I need to check my phone real quick. Okay, sure. All right, cool. What was I doing? Yes, so while the childs exist, we need to check to see if the child has the value that we're looking for. So while child, so if that means child exists, we're going to say, hey, child, if child dot val equals the value we're looking for. Well, if we found it, then we know we need to do something. We know we need to keep a reference to the next. So this is going to be a const. This is child next ref equals child dot next, which could be null, but again, that's we need to keep whatever it is, and then we will set the parent dot next to that child reference. And the reason why I'm keeping the child reference. No, hold on, I'm doing something wrong here. Oh, this always gets confused because you have to like keep references to things. So child, I'm just gonna like do it outright, and if I bump into a problem, then I'll just go back. So parent.next equals to child.next, right? Okay. So that means the child there's no way of referencing the child outside of this. So I will eventually need to return child here. I can return child here actually, because I found the value. So I don't need to do that here. I can do it. Well, I can do it there too. Hold on. I'm not gonna do that right now. Okay. So you have the child.next, and you return the child, but we need to set the child.next reference to null, because we don't want it to be able to like reference things. We just want to like extract that node. It has nothing can reference it, and it can reference nothing else. So it's just like a standalone node. So I want to do that. Yeah, it's fine. It's fine. So if other things that are coming to my mind are the fact that this value, maybe it's a node reference itself. So I might want to have to check to see, is this val thing actually just a number value, the actual value, or is it a reference to a node itself, which would be easy enough to implement, but just something to keep in mind. Okay, so you reset the parent. So the parent now references the child next. The child itself has been extracted. There's nothing referencing it, and it has a null reference to a next. So it is literally just standalone by itself. You can return that, and you should be good. All right. The else situation, which doesn't matter because it'll return, so you don't need to have an else statement here. That is done there. Then here we can say, okay, well, we just need to say parent equals child, and child equals parent.next. I think that will work. And if you get to this point, so if you get out of this, that means that nothing was found. Nothing found, value doesn't exist. So should I throw an error? I'm just gonna return no. Okay, coolios. So that stuff works. I'm going to do a ll.delete the number 30. And then I want to console log ll.root as just to see what that looks like. Okay, let's see what that looks like. So console log this. Oh, right, doesn't work. Delete is not a function. Delete is not a function? Delete is a function. What? Delete val? Oh my goodness, I can't spell for my life. And why am I like debating with the computer? The computer doesn't do it. It knows what it's doing more than I do. So here I have my node that's kind of like a detached node. And then I have my reference here. So actually I don't want to, let me kill a few of these. Let's delete the 10th. All right, because I want to see the whole thing. So 10 is here, and then the reference is from 5 to 20, and this looks like it's working the way it's supposed to. I'm going to delete a few things. So I'm going to delete that, 20, and I want to delete 5 too. So I'm going to have an empty root in theory, right? Yeah, my root here is empty here. So when I add, so I want to add 45, it should now add that to the root. And I want to do this, hold on. I want to just like do it here and then do my root here. Look at my root after that. Hello. Oh, add is not a function. What did I call it as? Append? Probably append. Yeah, of course. Appends. Okay, and here I have my 45. So I reset the root. So I did take that into account with the sort of edge case where root doesn't get defined at all. It allows for it right here. Okay. And get kth. Let's see if that works. Get kth. Get kth. I want the 10th to last, and it should give me null. No, perfect. Okay, cool. So I consider this to be a semi-victory because it actually worked without too much craziness. I think I mentioned in the last video that my first technical interview, they had me make a linked list, although that's not the name they use, and I wasn't familiar with data structures, so it went pretty much as horribly as it possibly could have. And after that, I read up on data structures and specifically linked lists, and I learned about it. So that was my first foray into the world of tech and technical interviews. So I think I have, but this is probably like one of my stronger data structures I know and have familiarity with. Anyway, that's it for now. I will catch you in the next video, which should be about stacks. Oh, big O notation. I didn't think about that. So let me go back here and talk about big O. Big O. I think it makes sense. I'm just gonna think about it on the fly. So for the space complexity, it's going to definitely take up n because that's just the number of items. For time complexity, it kind of depends. You will have to search through the whole list. So worst case, you have to go like O of n to just like find a value. I guess for lookup, for deleting, it's the same. For insertion, it's actually I didn't implement as insert. But I don't see it wouldn't be much different because you just need to find the place and then you insert on that. You just have to switch the references around. So that would be like one thing. If I were to add or change anything about this, I would definitely add in a method to insert after a particular value. So that would be what I do. And for the and for the best scenario is O of 1 because you can just reference the root or the tail end wherever you are, which would be as quick as it can be basically. So that's it for me for now. Hopefully that was useful, enjoyable. Maybe you were probably making fun of me because I can't spell. I need spell check for everything. And I will see you in. I'll see you in the next video. See you around.